everyone. Welcome to the fourth NCI and Intersect Showcase, AI and Machine Learning in Astrophysics. My name is Chris Power. I'm a Senior Principal Research Fellow at the International Centre for Radio Astronomy Research at the University of Western Australia. My research tackles dark matter and galaxy formation theory using supercomputer modelling. I will be the moderator for today's showcase. Now, let's welcome Satish Nair, the CEO of Intersect, to make some opening remarks.
Thanks, Chris. Good day, everybody, and a warm welcome to today's showcase. My name is Satish Nair, and I'm the CEO at Intersect, a co-host of today's event. Today's showcase is the fourth in a series of educational sessions that Intersect and NCI are collaborating on to provide further focused education for postgraduate level researchers. The subject of today's showcase is fascinating, as we often look up to the sky and wonder at its expanse. It's of particular interest to all those who are keen in learning about the use of AI and ML in understanding the working of the cosmos and unraveling new physics. I would like to thank the speakers for their time in sharing their knowledge, inspiring research, and raising awareness in this field. Also, a special thanks to Mayun from Intersect for her work in organizing this event. I'll not take any more time and hand over the chair of today's showcase, Professor Chris Power.
Thank you, Satish, for the opening remarks. In the showcase today, we are very fortunate to have four excellent speakers, internationally recognized for their leadership in AI and machine learning in astrophysics. So it's now time to introduce our second speaker, Ashley Villar. Ashley is an assistant professor of astronomy at Harvard University. She studies extragalactic transients, including supernovae, and develops statistical and deep learning methodologies for wide field surveys. Over to you, Ashley.
Great, thank you so much. I'm so excited to be here. Apologies, I will probably not be around for the panel because I will probably go to sleep. But you should be looking at my slideshow. I'm super excited to tell you a little bit about the research that my group is doing. So it's a fun complement and bridge between the talks, actually. So we study stars and the deaths of stars, which are called supernovae, but we don't do cosmology with those explosions. And I'll tell you a little bit more about why we care about stars that explode that don't just measure distances of our universe. And we do a lot of this, of course, with fun data-driven methodologies. Okay, and in particular tonight, I'm going to tell you a little bit about in this new era in which we just have a kind of an absurd amount of data available to us, we can start to ask questions of, well, is there something not in our physical bucket of knowledge that might be existing in the universe? And can we become sensitive to finding those new physical objects? And by that, I mean, we're looking for anomalies in the night sky. So first, let me tell you a little bit. My group does something called time domain astrophysics. And the way I like to describe this is to say that our universe evolves very, very slowly, as you probably know. So massive stars, for example, only live for millions of years. And to me as an astronomer, that's a very short amount of time. But of course, as a human, that's a very long amount of time. Time domain astrophysics really is the study of the universe on human timescales. So we're looking at the dynamic sky and how it changes on hours to weeks to months type of timescales. So what actually happens on those timescales? Actually a lot. One of our favorite things I've already mentioned are the deaths of stars themselves. In particular, I care a lot about how massive stars die. So this is kind of loops a little too much. So I'm going to go back for a second to talk about it. So these stars, I think there are astronomers in the audience, but for people who don't do astronomy, it turns out that stars live most of their life fusing elements into heavier and heavier elements. They kind of climb up the periodic table in this fusion process until we switch from an exothermic process that's producing heat to an endothermic process that unfortunately is eating up heat. So as a star, I'm continuously in this battle between gravity trying to pull me in, and luckily the exothermic processes of nuclear fusion that are pushing me out. When I turn into an endothermic process, then I end up actually collapsing in on myself, and I eventually bounce off for some interesting reasons, and I result in this interesting explosion. We see these explosions evolve on timescales that are dependent on the half-life of radioactive species that are formed in these explosions. And luckily, those are well-timed to human timescales. They can take weeks or months. And what's super fun about these, so supernovae, these explosions are so important for astronomy across the board. If you're not an astronomer, what I normally turn towards is to tell you that if you look at our periodic table and you color code it by the origin of these elements, very few elements are made in the beginning of the universe, the Big Bang itself. Really, that's hydrogen and helium. And basically everything else needs to be formed in the belly of a star. And the only way that I enrich the cosmos with that belly full is that I need to explode outwards. And so here I'm showing you that about half the periodic table, just above kind of the Iron Peak, is made either in the process of fusion of the star or during the explosion itself. I also just point out that the heavier I get, the more I need slightly more exotic forms of nucleosynthesis. And in particular, I end up needing really neutron-rich environments to make the very heavy elements. And we'll kind of touch upon that later on in the talk. So that's one reason why we really care about understanding these explosions. That's really a story of how these elements come to be, the elements that make up everything around us. It's not just that, though. Really, supernovae, especially massive stars, touch upon many areas of astrophysics. So one you've heard a lot about indirectly, cosmology. The explosions of white dwarf stars, a particular type, end up all looking pretty similar. So we call them standardizable or standard candles, which just means that because we know what the intrinsic luminosity or the wattage is, then we can really use them to measure distances. And that's how we famously use them to measure the expansion of the universe. But not just that, massive stars are also dominating the light we see from other galaxies. So if we want to understand those galaxies and how galaxies are generically formed in our universe, we really have to understand the stellar populations themselves, especially those of massive stars. So time domains, very fun, very important. Our group thinks a lot about the explosions themselves or eruptions, anything varying. And what I really love about the field of time domain astrophysics is that we get to explore such a fun, wide variety of high energy astrophysics that really does span an incredible dynamic scale in observational physics. So I'm showing you here a cartoon plot where I'm just showing how long something lasts very loosely versus how bright it is. Astronomers have this really goofy unit of measuring how bright something is called a magnitude, but just so you know, a more negative thing means it's brighter and it's on a logarithmic scale. What I really want to show you though is that when we look at the night sky, we see changes in the fluxes or the luminosity that we actually observe, and those changes can last for a very long time and be quite bright. In the case of having some physics that has a very rich reservoir of energy. So for example, if a supermassive black hole at the center of a galaxy far away from our own is actively accreting gas, I might be able to actually see a thermalization of that accretion in the form of what's called an active galactic nuclei. And that, like I said, that can last for like years and be incredibly bright. In contrast, I might have something like the merger of two super, super dense stars called neutron stars. And when they merge, they form these, actually, we mentioned this, these very heavy elements that are radioactive. And as those decay, I can see a very little, a somewhat dim and short-lived transient that we call a kilonova. So this is all to say this span exists in the universe and it's happening all the time around us. And we are, in a sense, just given those observations, and it's up to us to kind of put it on these plots. So that was our cartoon, but I really do want to emphasize that there's a sense in which this is the name of the game, that we have observables, that we see them in real time, and we attempt to organize them into their very disparate physical sources. In reality, these things heavily overlap in this kind of feature space I've made for you. A ton of these things, especially those supernovae, which are powered by radioactive materials, kind of all overlap with each other because they're all kind of driven by the same power source. So it's actually really hard to hand engineer these features to figure out how I can pluck out the different classes or types of physics available. This is a really, as all astrophysics is, it's a really old field. And so we have this incredibly, at this point, elaborate taxonomy and that we use to describe the physics that we see. I'm just going to give you a hint of this. Normally, to classify these transient objects, meaning they show up and disappear, they're transient phenomena, so like supernovae, we take a spectrum and then we just ask questions like, what elements am I able to see that are being excited in some way in that spectrum? And a really common one we have is like hydrogen. And that's an observable statement, but it really does connect back to the physics. So for example, if I see something that looks like the explosion of a star, if I see hydrogen, it means that that star has retained some hydrogen envelope, just like our own sun, although to be clear, more massive. And that's opposed to something where if I don't see hydrogen, but it's an explosion, then suddenly I can guess, whoa, somehow this star got stripped at some point. And so maybe that indicates that it's a white dwarf, like a type 1a, and I can use it to do cosmology. The more we find supernovae, though, I'll just kind of skip a slide, the more confusing this taxonomy gets. It really is this to me, very fun web of possible physics that's telling you the story of each individual star's life. And the way, what do I want to say? The features that we see in these explosions is kind of a combination of ingredients of what's actually the power source driving the explosion. Did the star have a buddy, like a binary companion throughout his life? And how did the star interact with its local environment? Did it kind of pollute it with material, or is it living in a clean environment? And all of this comes together to as a visual, what do I want to say, as a visual feature set that we see in the night sky. Okay, so our goal is to look at this kind of zoo and untangle the life story of these massive stars. So how do we actually do this? I keep saying like it's something that we visually see. It really is. So what we do is we have these wonderful robots that are attached to telescopes, and every night they look at patches of the sky and they look for differences or changes in the night sky. So here I'm showing you a picture of a spiral galaxy, and that wonderful green arrow tells us where the new star shows up, and that's a supernova happening in that galaxy. And what we do is we, in automated ways, we find these new explosions, and then we kind of track them over time. And we make decisions in real time if we want to go get more observations to really understand that physics, or if we want to just let it move, if we want to move on, keep the data in our archives. I'm going to tell you a slightly bit more about this. So I'm showing you a very similar picture here. I think it's just a simulation. Peter, who's on the call, will know that this is another kind of picture I'm showing you of the star itself. We don't use these pictures directly. Instead, we do one of two things. So the first thing we can do is to take a spectrum over time. And if we were to do that, we would see something like this GIF, where I'm showing you, it's a spectrum. I'm showing you the flux on the y-axis and the wavelength of those photons, or the color, in the x-axis, and time represents time. And so you can see there's a lot of really fun structure here temporally and in this kind of wavelength space that's telling us a ton about the makeup of the supernova itself, its energetics, and the progenitor star that led to this. In practice, this ends up being, we can't make these GIFs. They're really expensive. And so we end up making low resolution versions. So we basically just say, and instead of getting every single wavelength, which is hard to do, I'm going to just look at, I'm going to group together all the blue photons and all the red photons. So I'm going to plot those over time. We call that a light curve. And that's what I'm showing here. So that's basically, imagine it's like the green area as a function in time. It still captures the physics, but it's a low fidelity kind of version of it. Okay, so that's the data we have in hand. And I want to emphasize that we have lots of this data, which is very fun. So supernovae have been pretty well studied for about a century now and like classified, and we've been trying to tell this story. Really only recently have we been finding them in a number that I would call big data. So here I'm showing you just a plot that's a histogram in log axis. As a function, let's see, how many supernovae are we discovering per year, starting in the 1980s, where we found like a dozen per year, which is pretty good. That's why I'm showing this light blue shaded plot. And you can see that that discovery rate has been growing exponentially with time. And nowadays, we find about 10,000 of these events every single year, which is pretty cool. I do want to note that the taxonomy I showed you, that tree, is very much based on spectroscopy. So really getting a sense of all these little wiggles in the line. So we can say things like, do I or do I not have hydrogen? The gray line is showing you kind of the fraction that's actually getting one spectrum that we're using for classification. And you'll notice that that has also been increasing exponentially, but unfortunately, we're doing a lot worse now. So unfortunately, we only get about 10 to maybe 20% of all supernovae we discover get like a traditional label on them. And most of them just go to our archives. And to be honest, we don't do a ton of science with those right now. I will say that the game is going to change. I'll tell you why it's going to change in terms of numbers, but I'm not going to talk in this talk at all about the many fun problems of how do we classify things? How do you do like Bayesian hierarchical? How do you do population modeling with ones where it's all probabilistic? I'm not going to talk about that. I'm going to talk about kind of the fun, what happens when we find tons and tons of things, and how do you find the most fun events to follow up? Okay, so this is the state of the field right now, which is great. It's pretty data rich, although maybe if you're a true ML person, you might think that's not that much data, which is fair. What's really exciting is that very soon there's a new observatory that was mentioned that's going to come online. It's called the Vera C Rubin Observatory that's actively being built in Chile and is a joint project between Chile and the United States through National Science Foundation. That is an incredibly large telescope that's going to begin a 10-year-long survey of the southern sky, where by survey, I mean it's taking like a really low cadence movie of the southern sky. So every few nights, it's going to take pictures in the same place, and we're going to be able to ask the question, do I see new stars showing up in that place? What's super cool about this is that because it's a wonderful mix of being incredibly sensitive that we get the deepest images we've ever gotten over the widest area we've ever gotten. It really is the entire southern sky into this just like truly unprecedented depth from the ground. So what's fun is that this is very much going to become a discovery machine and change the status quo of that plot I just showed you. So I'm waiting for a GIF I have to reset. Perfect. So I'm showing you the same plot, but now in this arrow, I'm showing you what happens in a few years when Vera Rubin comes online. And as you can see, it's very dramatic. It's partially dramatic because I made it linear scale, but I really want to emphasize like it really is super dramatic. So it's the same plot here, but you can see this arrow takes us up to an annual discovery rate of these explosions to 1 million per year, which is a break from exponential growth by about 2 orders of magnitude, which is so wild. It really is going to be this big data explosion that we're really excited about. I do want to point out that as this happens, there are some really wonderful efforts to help us also get follow-up. So to help us, when we find supernovae that we really want to study in real time before they go away forever, there are efforts to try to get those kind of spectroscopic resources. It's really hard to match the increase that LSST or the Vera Rubin Observatory is going to bring us. And so the fraction of events we can follow up in real time is going to drop from 10% to something like 1%. So it's really going to become a very selective field of what science is meaningful enough to be doing in real time with very scarce resources. I'm going to spend a few slides just like emphasizing how important this problem is. We are in, I love to use the metaphor that there's a needle in a haystack problem. The haystack is the million of explosions we see per year from this observatory. And from that, I can only get a spectrum, so like one additional observation of, let's say, thousands per year, which is about right. And so even that's rough. But even from that, really the limiting resources is human power. We don't have that many astronomers. We don't have that many PhD candidates that can help us trigger the observations, write the papers, do the studies in real time. So I can optimistically guess, maybe our community will, in detail, follow up, understand, analyze 100 interesting supernovae per year. Math, 100 in a million, is roughly like saying about 1 in 10,000 supernovae can be studied in real time. So get any additional data on it. And what's kind of fun, scary, interesting, I don't know, about this is that that ratio is 1 in 10,000, or in other words, if we find 10,000 supernovae in 2024, this year, it's literally as if my entire community had a conference in which we decided which supernova of all of them we were all going to devote our time to this year. Like it's such a different way of thinking about this field, and what does it even mean to be important enough to follow in real time? Okay. So I'll say I have a super biased opinion because I don't do cosmology and I study the this kind of fun life and death of stars. And so I very much think that we should think a lot about the unknowns. We finally have a chance to find a 1 in a million or a 1 in 10,000 type of event. Very rare high energy astrophysics. And I think what's so exciting about this is that it really does mean that even for the most rare events, the things where we found one of them this year are suddenly going to become so commonplace that we shouldn't follow them up. Everything we know about now essentially isn't, this is controversial, but to me, might not be worth the resources of following them up because they're so commonplace and we only get one shot with each of these explosions. So I think we really do need to prepare to ask the question, what's the unknown unknown that might be sitting in the data? And importantly, how do you become sensitive to that? How do I know if I literally don't know what I'm looking for? How can I find it? Okay. I'm going to go on a tangent here that's a bit physics or astrophysics focused. So for astronomers in the call, I think this will speak more to you. You might be asking, like, why? Why do I care about these weirdos? Why do they matter? So the weirdos really do probe hot, exotic high energy physics that is theorized, but just impossible to be testing terrestrially, but still might have very strong implications on how our cosmos is evolving. So I'm just going to give one example of a theorized event that would be a 1 in 1 million type of observation. And this is where, gosh, all of my GIFs are kind of blinky, so I apologize for that. This is now going back to when I talked about the periodic table. I mentioned that those really heavy elements require really neutron-rich environments. I'm going to talk a little bit about why that is. And I'm setting you up for this by showing you a fun GIF of 2 neutron stars, which are very neutron-rich, hitting each other and forming these heavy elements. So the reason why these neutron-rich environments are so important is because to get to the heavy elements, we really need we need to have some form of a neutron capture process. In other words, I need to be sitting around as a seed nuclei, just meaning an atom with my neutrons and protons. And if I want to go up the periodic table, I need to be gaining protons, not just mass. But it turns out if I like throw a proton onto me, suddenly I have a charge and I don't really want to add more protons to myself. So one thing I could do instead is I could throw a bunch of neutrons on me. That gains mass, but until it beta decays, I can't actually turn that into a proton. That being said, though, I'm able to gain mass very quickly and to go up the periodic table if multiple of those kind of turn into protons. Okay, so that is to say that let's see, how do I want to say it? These neutron-rich environments allow something called the rapid neutron capture process to occur, in which I can, as a seed nuclei, gain many, many protons. They'll beta decay away, but then I've actually moved highly up the periodic table by gaining all of that mass. There are very few environments in which I can have such a neutron-rich arena that I can actually have the rapid neutron capture process occur. A really obvious one, theorists, is the collision of two neutron stars. And in fact, a few years ago now, in 2017, thanks to the gravitational wave detectors, LIGO, Virgo, we did detect gravitational waves from these merging neutron stars. And we pointed our telescopes and we were able to see the rapid decay of heavy elements that are consistent with models of rapid neutron capture process decay. So we know that at least one site, astrophysically, that can create heavy elements is the collision of neutron stars. There's lots of reasons astrophysically, though, to think that that's not the only site, and that there might be weirder, more exotic locations. This is a super confusing plot, and so I've just added labels for you. There's a really nice review about where do all the elements come from. That's why I took this from. But what I'm trying to show you here in this confusing plot is that when we look at stars in our Milky Way, we notice that, how do I want to phrase it? We notice that for some reason, there seems to be a lot of really heavy elements in stars that aren't old enough to be consistent with having neutron star mergers. Why is that? Because naively, neutron star mergers, so that is two neutron stars orbiting each other, the only way that they can come together is by losing energy in their orbit via gravitational waves. And that's like not an efficient process. And so it ends up just taking forever, basically. It takes billions of years for those things to actually lose enough energy to hit each other. And so we expect in general, there's a very big lead time between when I form the stars and when the things hit each other. So I don't expect really early stars to have these heavy elements, and yet we do see it. And so that's a confusing point if we think that all heavy elements are coming from these neutron stars hitting each other. Okay, so that kind of spurred some ideas of how else can you make this really quickly. One way you can make this quite quickly, and this is the exotic, have never been seen before, completely theorized to be clear, idea is that, well, maybe really massive stars in very specialized conditions, so if they form a black hole and it's spinning and has this accretion disk, it actually turns out that you can make an environment in which I actually do make heavy elements. And in fact, so working with, this is a while ago now, working with Daniel Siegel and Brian Metzger and Jenny Barnes, we theorized this model in which actually some of the earliest stars, which are incredibly massive, might actually form some of these heavy elements and can produce a ton of heavy elements, like up to 10 times the mass of our sun in these explosions. They'd be super, super, super rare, because one, if they weren't rare, we would have probably seen it by now. But two, also just the odds at which you have such a heavy mass star and it's spinning, its luminosity, all that factored together means that it's probably a pretty rare population. But we actually did run the numbers, and we do predict that you'll find about one per year in the Vera Rubin Observatory survey, that 10-year-long survey. And so this is a good example of if you found this, what a fun smoking gun signature that really solves this question of astrophysics right now. Why in the world do we have quickly forming heavy elements? But it is something that is such a weirdo. It's such an anomaly, and it's definitely incredibly rare to find. Okay, so that was a fun physics aside, mainly for entertainment, to tell you that there is reason to really care about these weirdos. Now I'm going to shift gears and talk a lot about, at a really high level though, the ML techniques that we're using to try to find these anomalies. First, I'm going to tell you what is an anomaly to me. And there's two anomalies that I think about, but there's only one that we're really sensitive to right now. So the one that we're sensitive to is probably the one that you think of and that I think of when we say anomaly, and that's an out of distribution anomaly. So here I'm showing you, let's get this great graphic of, pretend I see lots of supernovae on the sky. I see their light over time, and I have physical models where I can fit those physical models and infer properties of that explosion. In particular, I'm pretending that I can infer the energy of the explosion and the mass of the star that exploded. And here I'm just showing you, pretend I only know of two different types of stars that can explode, like white dwarfs and what are called red supergiants. It doesn't, none of this matters. It's just two types of stars, two types of explosions. I put it on a plot. Out of distribution anomalies are anomalies like this cow, and there's a reason I chose a cow, but I'm not going to tell you, where what we're really asking is, in this latent, or this unseen parameter space, so I don't directly see energy, my eyes can't see, they kind of can, they can see wavelength, but they can't see energy of the explosion. I have to infer that. So it's unseen to us. It's not like a feature I observe. It's actually a latent feature that I infer. So in this latent space, I've seen many supernovae, and I've seen enough where I can actually have a density estimate, and I can say, oh yeah, I definitely see a lot here and here. And out of distribution anomalies are ones where I say, I'm in a really low density region. Very few things seem to happen here, like this cow. And the way that my field has primarily looked for these things is actually super easy. So we make these kind of latent spaces, and then we just ask the question, who amongst these points is in a low density region? So to do that, I use something called and we all do in the field, we use something called an isolation forest. That's pretty easy to understand. I take my latent space, I make a random cut in one of the features, like energy, and I just say, I'm going to make a cut here. And then I subdivide the space into the left side and the right-hand side. I make a second cut, let's just say here, but only in one of these dimensions, and now I have kind of these three sectors. I keep making cuts, blah, blah, blah. And as I keep making cuts, I can ask questions like, hey, how many cuts did it take to put this cow in its own space versus how many cuts does it take to put, oh gosh, I don't even have one, this guy in his own space. For this guy, it took many, many cuts to get him in his own space. And for the cow, it took very few cuts to make him in his own space. So in a sense, the number of cuts it takes, or the number of branching decision trees I need, inversely tells me about how weird I must be. If I don't take a lot of cuts to isolate me, I'm probably pretty weird. But if I take many, many, many cuts like I do here, I'm probably sitting smack dab in the middle of my distribution. I'm probably not very weird at all. So that's how we find these anomalies. I just want to point out briefly, and I don't have a slide, okay, about the physics of this. I want to point out that there are other types of anomalies. The only other one I want to mention is this idea of a contextual anomaly, where maybe I'm in this like red regime, but suddenly I see something that I thought should look red, but it looks like this catfish instead. And the idea there is, well, in the context, I expect X, but I actually see Y happen. And this is also very interesting physically. I just want to be clear about that. But everything I'm talking about is not sensitive to those types of anomalies because they're in high density regions in this particular latent space, and so I can't select them. But it's a very fun problem to think about. Okay. So in this description, I talked about this latent space that was very physically informed. I said one dimension I'm going to call energy, and one dimension I'm going to call mass of the star that exploded. And to get those, I'm going to fit lots of models to my explosions. I will say it's actually not trivial to generate that space. And in fact, it's not possible to generate that space. Why is that? Because, as I mentioned earlier, the cosmos is a zoo of high energy phenomena. Some of these events that I meant, even the ones I mentioned, like the supermassive black hole eating gas onto it, what is the mass of the star? It's a black hole. It doesn't make any sense. What's the energy? It doesn't make any sense. There is no one model that I can just write down to describe all physics I see. It's not possible. And the diversity I see is in some way, almost by definition with anomalies, I can't know it a priori. And so because of this, we more often than not turn to a very physics-agnostic version of these same plots, where we build up our latent spaces using fully data-driven methodologies. And these were kind of mentioned before, and I'll just talk a little bit about autoencoders. But the idea is that I have these time series, and I just want to find a latent space, so some vector space, where I can embed these physical data streams into to help me still make these types of plots and to do this type of analysis like an isolation forest. But I need to make it physics agnostic because I don't have a model that I can use. Okay. So I'll just say that one of the ways that we've been doing this in at least my group is we think a lot about autoencoders. What do I want to say? I think this group knows a lot about machine learning, so I probably don't need to talk too much about this. I think what I just want to maybe say in a jargony way is that what's fun to me about my field is that, and I've really glanced over a lot of this, is that we have interesting multivariate time series that tend to be sparse and irregularly sampled, that we need to coherently encode into fixed dimensional latent spaces. And so because of that, we typically turn towards these autoencoders where we can explicitly encode things like the time lag between observations and in what filter or in what wavelength we actually observe the photons in. Oh yeah, okay, I guess I didn't do this. I'll also just mention that for this anomaly detection work, we also typically use just kind of a vanilla, but a variational form of this, so a variational autoencoder. So you know, I think that variational autoencoders don't just build up a latent space, you also get kind of an uncertainty on top of that. But more importantly, and I'll show why this matters, is that we get some regularization on this space to make it continuous to help us with our density estimates. Okay, so I think I said this already, I forget. So right, because we have data coming in real time every night, we do try to, we build these in a recurrent way where we can update the encoded vectors, so how we're embedding each light curve, or the data that we see in real time. I just like to show this series of slides that shows you an example, and in case you don't know how autoencoders work, it doesn't really matter. The key point here is that, so what we do is we have some method, this neural network, that looks at data we observed. That's why I'm showing you in these points. So the point represents the observation, and this error bar is the uncertainty. And again, remember this weird unit, this is just representing how bright something is, where this is brighter at the top and it's dimmer at the bottom versus time. Okay, so those are the points. And then the lines are showing you what this autoencoder predicts the light curve, the data should look like, so the explosion should look like as a function in time. And what's interesting is that with very little data, we are able to make predictions that seem consistent with what we expect physically for these type of explosions. So it hits roughly the right magnitude. I'll just go ahead. And so without even specifying the physical model, we get something that looks roughly right. And I'll say, you know, it's pretty old. At this point, we do much better than what I did a few years ago. So that's great. The reason why we do this is because we're able to build these models by just showing in a totally unsupervised way this autoencoder many explosions from the night sky, and it's able to build up a representation of these supernovae and reproduce the data, and importantly, build up that latent space so that we can start to ask, where are the interesting anomalies? So we can take many supernovae, which is what I'm showing you in this scatter plot. We can encode all of them into these somewhat, you know, not meaningful features. They're not, this isn't a physically, I want to be very clear, we're not interpreting this as anything, but we can build up these latent spaces. And because we've used this nice vanilla variational autoencoder, as we know, our KL divergence with the normal distribution encourages it to be centered on 0 with a standard deviation of 1. And that makes a nice continuous density distribution. And we can ask simple questions like, hey, which of these points are in a low density region? And that's what I've marked in purple. And so what's fun about this is that I can try to find these interesting anomalies in real time. So we did this a bit ago now with a big simulation of the Vera Rubin Observatory. So there was this like really wonderful community effort that I always love to highlight called Plastic. It was a Kaggle competition run by like Renee Holtchek, Rick Kessler, and Gautam Narayan, amongst many others, that said, let's come together, put all of our physical models together and try to simulate the night sky, and then take a guess on what it's going to look like. So of course we can't simulate unknown physics, but what we're able to show here, at least, is that for this autoencoder-based method, we do in fact flag, I mean, I guess you're gonna have to take my word for it, there's a lot to take in at once. We do flag in general the minority classes, so the more rare physics, as being more anomalous, which is really exciting. And I think one thing that's very fun is that we can look at the very rare types of supernovae in the simulation. So here I'm showing you one, it's called superluminous. I don't have to describe the physics. And we can watch as a function of time that weirdness score from the isolation forest evolving. And we can ask a question, at what time in its evolution, so at each time point we re-embed it into the space, we can ask at what point does that weirdness score start to become the highest percentile? I don't forget, honestly, if this is like 1%, 0.1%, I just don't remember. And you could imagine that we would have triggered our telescope. And what's so fun is that in this case, we would have triggered our telescope very early, which means we would have gotten a really nice data set to really understand this type of event. And what's happening in time is that, so in black, I'm showing you just the full sample of supernovae. These purple points all represent this one weirdo, but the darker color, let's see, the coloring of these dots gets darker with time. So in other words, you actually kind of watch it walk away from the distribution as it becomes weirder and weirder according to this isolation forest score. So the embedding really does, as I become less prior dominated and I have more data available, I can kind of see me move away. So that's super fun. So let's see, what do I want to say about this? This has been really exciting. It means that there is a path forward using pretty standard ML techniques that are in many ways physics agnostic to find new physics. We have kept working on that since then, so I'll tell you a little tiny bit about what we've been doing. Most recently, through something called the Young Supernova Experiment, which is another survey of the northern sky, actually, that's happening right now, we have been building active anomaly detection algorithms that are running on real data, not simulations. And in particular, so this is really great work by Patrick Aleo, who just graduated from UIUC. What we do is we take our data, the explosions we see in the night sky in real time, and we also take the picture of the galaxy they exploded in. And we put both of those pieces of information, so the image and the time series, into the same joint embedding space. And then in that embedding space, we actually ask like a few tasks from that. We do things like we ask for, well, we're not doing classification right now, but we ask for nearest neighbors, which I'll show you in a bit. And we also do ask for things like what is sitting in a low density region? What's an anomaly right now that we can find in real time? So what do we actually find? So apologies, like it's hard to describe all the physics at once, so I'll just say a few things about it. Let's see. This one, unless you're an expert on supernova science, it's not going to look weird to you, but it is weird. So here's a fun event that came from what's called the Zwicky Transient Facility. That is just an ongoing northern survey that's looking at the night sky. This supernova is weird for a reason I'll describe in 1 second. It's called a type 1b. That just means that this is a massive star that has, for some reason, lost its, so massive stars are like onions and they get heavier and heavier elements with each inner layer. This star has lost its hydrogen envelope, but it still has retained some of the helium right under that. So it's got like its little second onion layer still. That's not so weird. These things are kind of rare, but not incredibly rare. But what's so fun about this one, though, is that it has this incredibly asymmetric shape that's very unusual for these types of supernovae. So what's fun is that this was noted as incredibly anomalous pretty early on, and we were also able to get a spectrum early on, although had we had this running, we would have been able to trigger much earlier and really understand what's driving this early emission that we see in this supernova. Because we do this kind of joint embedding space, we can also ask for contextual anomalies, meaning looking at the environment the supernova is living in, is that something that looks strange? And here I'm just showing you some fun examples. I tried my very best to turn up the contrast on these, but these are fun because these are pictures of the galaxies that these interesting supernovae lived within. And these are both these halo galaxies. So you can kind of see here, there's this weird blue ring. And you can barely see this. There's a blue ring here too. So these are very strange. They're probably from mergers, and these are these rings of intense star formation and massive stars. And these supernovae are occurring in these. And so these stick out because it's not that the supernova looks strange, but the environment it occurred in was incredibly odd looking. Okay, and so I will say in real time, the way this works, which is quite fun. So anyone can access this data. It's living online right now through something called the Antares broker. But we, as a collaboration, this young supernova collaboration, actually every day, like 9 a.m., it's very fun when I sit down with my coffee, we get a Slack bot alert that tells us about the most anomalous candidates that we have. And it has an active feedback loop that we're not using yet, but we're hoping to use soon, where we actually do kind of, you can see at the bottom here, we upvote whether or not we think it's anomalous, or if we think it's this other, we're not so interested in these things called HGNs. We also kind of make notes if it's that. So we do have these kind of bots that aggregate the information, they actively filter out these anomalies, and then send us the top 3 candidates every day. I also just want to mention in passing, what's so fun about these kind of embedding what's fun about doing representation learning that builds up these latent spaces is that you can ask questions of the latent space that are hard to formalize otherwise. So by that, I mean, you can do things like a nearest neighbor search. So one thing you can do in this LACE methodology is that you can say, hey, I have an event that looks like this. Sorry, this is a little hard to see, but in this plot, which is the light from the supernova as a function in time, you can see these bright red points as opposed to these dim red points, and these bright green versus these like low opacity green. These bright red and the bright green are from one supernova, this guy, who also came from this galaxy. Everything else is actually the nearest neighbor from it. And so we look for events that have both similar homes that they're from, the galaxies themselves, and light curves. And so I think what's really exciting is that in the era of something like Vera Rubin, when we find these really anomalous guys, we can ask questions like, okay, you might be in a low density region, but who is your nearest neighbor? Is there a class that can emerge from these kind of very sparse areas? And then I'll just say one more thing, which was mentioned. Foundation models are definitely all the rage. And it's also very much all the rage in time domain astrophysics. So we are really thinking a lot about these representation spaces that are multimodal, that use these images, that use these time series, and that use spectroscopy all together. And one way I've been thinking about this a lot is thinking about this multi-view, this multimodal view of the data as kind of your back end to how we talk to data, how we mind map and organize it. And in the front end, we're pairing this with large language models. So apologies, it's a little bit blurry, but we pair it with large language models via chatbots where we can actually ask questions via SQL queries of the database we have. And we can pair that with RAG to actually give it some astrophysical context of the physics we might be interested in. So I really want to highlight that this work is done by a really wonderful postdoc, Alex Gagliano, who's an I5 fellow, joint between MIT and Harvard with my group, who has been working on this fun chatbot called the Speakeasy for the Young Supernova experiment. Okay, so I'm going to end there and just say that I hope I've excited you a little bit about finding these really fun anomalies in our kind of cosmic haystacks. And I want to just, if it's okay, end to say that in my intro, I think it was mentioned that I'm part of a science collaboration called the LSST, Informatics and Statistics Science Collaboration. If you are interested at all in some of this work, you are welcome to join. Anyone who's in data science or astrophysics is able to become a member and work on some of these fun problems with our astrophysical data. So I'll end there and take questions. Thanks.
That's great, Ashley. Thank you. That was a really, really cool talk. So we don't have any questions in the Q&A yet. I'd invite people to enter their questions and we can ask Ashley. I'd also invite people to raise their hands if they want to ask a specific question. While we wait for that, Ashley, one of the things that came out from the talk was how this data-driven approach allows you to identify features in latent parameter space. So it looks like that theory may need to play a bit of catch up here. How exactly do you foresee the theoretical interpretation interacting with the approach that you're taking so far?
Yeah, that's fair. You're totally right. I actually see them as running in parallel. So there's this kind of there's the broader question of how do stars live and die and what's driving their explosions? That has to be paired with traditional statistics. Like it just has to be. But there is a sense, this was mentioned, uncertainty quantification from these ML methodologies is so necessary to answer that. And that's something that we're very actively working on. And it's challenging because there is systematic uncertainty where the theory truly does not match the physics we see. Explosions are really complicated. That's kind of aside from just finding the cool things that we really don't know about. And there's kind of an expectation that, of course, we don't have the theory, but we're hoping first and foremost to get all the data we can get so that we can build models around that data.
Okay. Any questions from the audience for Ashley? Okay, well, if not, oh, okay, great. So Fatima Hafezian, thank you for your talk, Ashley. It was great and interesting. What was the name of the group that we can collaborate related to Astro and ML? Yeah, I can see you're answering now. So I guess that's the LSST group.
I'm typing it just so it's really clear. Yeah, so that is the LSST. Do they work? Oh.
Oh, the count.
I
From
can't
Lorenzo
explain that.
Campoli.
Yeah. So I will just say that yeah, everyone's welcome to join that group. It's, again, very much open to professional data scientists or astronomers, and it's very fun to play with astro data, in my opinion. It's very fun if you're interested on open source software or problems. The cow is kind of goofy, so it is a funny story. So the way we actually name our supernovae, but we name them just based on the year and then alphabetical count up. So we start with 2024 A and then B, blah, blah, blah. So we find so many that we get to like several letters. And so I will note that it gets kind of goofy a lot. And so very famously, there is this one event called 2018 COW, or the cow, that really was this oddball anomaly that we still don't know what the origin was. It was very, very fast and very bright, which is actually where the cow was sitting in my little feature space. But that's where the name comes from. It just happened to be COW.
Thanks for clearing that up, Ashley.
Yeah.
Okay, are there any other questions from the audience? Okay, well, if not, I'd like to thank you again, Ashley. Oh, one more just now. Is the large language model continually being updated?
Yeah, that's a really good question. So yes, I think everyone who's Yuan-san, actually, maybe I shouldn't speak for you. I assume Yuan-san's going to talk a little bit about LLMs. He does a lot of work with them. Yeah, we update them as new open source models come out, which, as probably everyone here knows, is like roughly every 6 months, if not faster, and it's kind of wild. So yeah, we do update that way. We don't do active learning though, as in we don't actively fine tune with the users. We just use the context windows that are typical in these large language models.
Hi, FNV. Thanks you for the talk, Ashley. Why VAE, an autoencoder or a PCA could be okay?
Yeah, the autoencoder. So actually, I'll start with PCA. The reason why PCA is not the most obvious thing to do, and this is actually a place where it helps to know a little bit about the physics. So as I tune up linearly a physical parameter like mass, I expect to stretch out my data in a nonlinear way. So I very naturally expect that there must be some kind of nonlinear space I want to embed into. Okay, so that's a reason to not choose PCA. And then autoencoders are totally fine if you want to do things like classification. In this particular case, we really wanted to do anomaly detection. So we really actually wanted this continuous dense distribution, which is why we chose a variational autoencoder.
Okay, thanks for that. Any more questions? People can also raise their hand if they want to ask Ashley directly. Okay. I'm not hearing anything else. So thanks, Ashley. We'll let you get to bed. I know it's pretty late there.
Yeah, thanks so much.
Yeah,
Chris,
thanks for that. That was fantastic.
Chris, there's a question. So Chris, Eric Miller has a question.
Oh, okay, sure. Eric, do you want to speak?
Sorry, yes, I think it's just unmuted me now. Sorry, that was actually a misclick on my end. Apologies.
That's okay, no problem.
Thanks anyway for the great talk.
Okay, thanks, Eric. Okay, well, I guess, yeah, I thought with that, we can say goodbye, Ashley. Yeah, have a good sleep, and yeah, thanks for the great talk.